We're now going to look at how we can describe the energy of a satellite in a stable orbit. So the mechanical energy of a satellite in a stable orbit isn't changing. Remember that mechanical energy is given as the sum of the potential energy plus the kinetic energy. So we can write the mechanical energy E is equal to U plus K. Now, this is true for any satellite in a stable orbit. If a satellite begins to drop and gets into the region where there's an atmosphere and so air resistance, then there'll be non-conservative forces doing work, air resistance in this case, and the total mechanical energy will start to decrease. So we've seen before that we can write the potential energy of a satellite in an orbit such as this as U is equal to minus G little m big M on R. Now in this formula, U is the potential energy, G is the universal gravitational constant, little m is the mass of the satellite, big M is the mass of the planet, and R is the distance between the center of mass of the planet and the satellite. Now, in order to obtain an expression for the kinetic energy, we can start with Newton's law for universal gravitation. F is equal to gmm on r squared. This is the only force that is acting on our satellite. So at the moment, we're looking at a satellite which is undergoing a circular orbit. So the acceleration of this satellite is the centripetal acceleration, which is given by v squared on r. And as the gravitational force is the only force acting on the satellite, it is responsible for this centripetal acceleration. So using Newton's second law, we can say, well, F is equal to ma. The a in this case is v squared on r, so we've got this is equal to mv squared on r, and the force which is acting is equal to gmm on r squared. Now we can do a little bit of rearranging of those last two terms now, and we can write, well, mv squared is equal to gmm on r, just by multiplying them both by little r. And this is useful because this is double the kinetic energy. So the kinetic energy K is equal to a half mv squared, which is equal to a half times gmm on r. So we've now got an expression for the kinetic energy of the satellite. From this expression, we can see that if the radius increases, the kinetic energy is actually going to decrease, so it's actually going to slow down. Now we can also calculate the total mechanical energy. So E is equal to U plus K, which is equal to minus gmm on R plus gmm on 2r, which when we add together, we get minus gmm on 2r, which happens to be minus k. Now, this was all derived for circular orbits. Many orbits, as we've seen, are actually elliptical. So how do we get the mechanical energy for elliptical orbit? Well, it turns out that we just replace our radius r with a semi-major axis length a. So the total mechanical energy of an orbit, an elliptical orbit, is given by gmm over 2a. You'll notice that there's no reference to the eccentricity in that formula, so it doesn't matter how eccentric the orbit is. What matters is the length of the semi-major axis. Let's have a look at a couple of problems that we can use these equations to solve now. So in this question, a satellite is in orbit around the Earth with radius r1. Mission Control wants to move it into a lower orbit with radius r2. With respect to the velocity of the satellite, in which direction should the thrusters fire? What will happen to the speed of the satellite? Okay, so to work out in which direction the thrusters will fire, we'll need to have a think about the work done on the satellite. And so we'll need to work that out. We'll need to look at the total energy of the satellite. So the change in the total energy is given by the final mechanical energy minus the initial mechanical energy. So using our formula for the total mechanical energy of a satellite, that E is equal to minus G little m big M on 2r, we can say that, well, this is equal to minus G little m big M on 2r2 minus G little m big M 2r1. So we can write this, giving it a common denominator on the bottom of 2r2 r1 as minus g little m big M r1 plus g little m big M times r2. So this is equal to gmm r2 minus r1 over 2r2 r1. Now r2 is less than r1 because we're told that it moves into a lower orbit. So by definition, r2 is less than r1. So if r2 is less than r1, the term on the top is negative, the term on the bottom is positive. So this is a negative. So this tells us that the mechanical energy decreases. So as the mechanical energy decreases, it tells us that we have to do negative work on the satellite, as we have to remove energy from it. So if we're doing negative work on the satellite, then the force must be in the opposite direction to the change in displacement, which is the velocity. So this tells us that the thrusters must fire in the opposite direction to V. Okay, now we get to the fun bit. What will happen to the speed of the satellite? Because just naively we would assume that if we were firing thrusters in the opposite direction to the direction we were going, that should cause us to slow down. But let's look at it in a bit more depth. We've got that our formula for the kinetic energy is equal to g mm on 2r. So our change in kinetic energy is equal to g mm over 2r2 minus g mm over 2r1. And this is equal to gmm r1 minus r2 over 2r1 r2. This is a positive number because r1 is bigger than r2. So the change in kinetic energy is positive. And so since the kinetic energy is increasing, the speed must actually be increasing. So it's a bit counterintuitive, but firing your thrusters in the opposite direction to what you're moving actually increases the speed, and that's actually because the radius decreases. Another way we can come up with this relationship is to use, gmm onto r is equal to a half mv squared. So cancelling out the m's and the 2's, we can see that v is equal to the square root of gm on r. So if we decrease the radius, we're increasing the speed. So the second question is, an astronaut releases a bowling ball of mass m equals 7.20 kilograms into a circular orbit about the Earth at an altitude of h equals 350 kilometers. Part A, what is the mechanical energy of the ball in its orbit? Part B, what is the mechanical energy, E0, of the ball on the launch pad at the Kennedy Space Center before launch? From then to launch, what is the change in the ball's mechanical energy? Okay, so for part E, we need to calculate the total mechanical energy of an object in orbit. So we will be using our equation that the mechanical energy is equal to minus g, the mass of the object, times the mass of the planet over 2r. Now r, that's the distance between the center of mass of the planet and the place where the object is. So we're told that this height is equal to 350 kilometers. So r is equal to the radius of the Earth, that's this distance, plus h. So let's substitute in our values. We've got g, this is equal to 6 6.673 times 10 to the minus 11. Little m, that's the mass of the object, which is the bowling ball, so that's 7.20. Big M, that's the mass of the planet, so that's the mass of the Earth in this case, which is 5.972 times 10 to the 24. And then we need to divide by 2 times this distance here, which is the radius of the Earth, which is 6.371 times 10 to the 6, plus the height above the Earth, which is 350 times 1,000. So solving this, we get minus 2.13 times 10 to the 8 joules, which we can write as minus 213 megajoules. Okay, part B then asks, what is the mechanical energy E0 of the ball on the launch pad at the Kennedy Space Center? Okay, so this is before launch, so we can't use this equation here for this part as the ball is not currently in orbit. So we're going to need to calculate E0 using the sum of the potential energy plus the kinetic energy. So we can calculate both these things. The potential energy is given by minus g m on r, and the radius in this case will just be the radius of the Earth. So let's put a little subscript e there because that's the distance of the bowling ball from the center of the Earth. And then we've got plus the kinetic energy, which is equal to a half mv squared. So the bowling ball is at rest on the launch pad, but the Earth is rotating about its axis, so it does have the Earth's velocity. So we can work out what that velocity is going to be. So the velocity is just given by distance over the time. So it covers one circumference, which is 2 pi times the radius of the Earth, in one day, which is 24 hours. So to calculate this, we've got 2 pi. The radius of the Earth is 6.371 times 10 to the 6, and then we've got 24 times 60 times 60, and solving this we have the speed of 463 meters per second, which is the speed that you are currently moving with about the center of the Earth. But we can then calculate the kinetic energy using a half mv squared. So this is a half times 7.2 times 463 squared, and this is equal to 7.7 times 10 to the 5 joules, which is actually less than 1 megajoule. Okay, so substituting in here, we've got minus 6.673 times 10 to the minus 11 times the little m, which is the 7.2, times the big M, which is the mass of the planet, 5.972 times 10 to the 24, divided by the radius of the planet, which is 6.371 times 10 to the 6. And then we've got plus this kinetic energy here, so plus this value here. So solving this, we get, for this term, we get minus 4.50 times 10 to the 8. Now this is much bigger than that. So the kinetic energy is actually negligible, so we don't actually need to include it. And so this is equal to minus 450 megajoules. So that's the potential energy that it has on the launch pad, and then it's got more potential energy because this is a less negative number once it's been launched. So in the last part, we're asked to calculate the change in the mechanical energy. So this is E in the orbit, which is what we calculated in part A, minus the initial mechanical energy, which is E0, which we just calculated here. So this is equal to minus 213 minus 450. So this is equal to 237 megajoules. So that's not actually an enormous number. So as the bowling ball goes from the surface of the Earth up into orbit, it's not gaining that much energy. This isn't what most of the work in launching a satellite goes into.